So my name is Jason Shepard, so I'm CEO of Atym, and this is my partner in crime, Steven, who's our CTO. And so today we're going to talk about a new project that we're donating code to Linux Foundation to seed, this Project Ocre, and we'll kind of walk through what it's all about. I kind of come at things from the IT side of the house. I was at Dell, and there was a company called Zadita that I was at most recently. We're like mini-me Zadita, and we'll kind of talk through how all that plays out. But I've been doing this for a while, past 10 years, have a lot of experience in open source, have launched several open source projects in Linux Foundation, chaired boards, and stuff like that. So this is kind of the next step as we see more and more compute going out into the field and kind of provide some context around that. But quick intro.
And so Steven Berard, CTO. I mostly from both the software and an IT background. Started my career at a company called APC where we did a lot of data center equipment, managing things over the network. Weren't calling it IoT at the time, but is a lot of the same concepts. Went through that, did some time at Microsoft, and then ended up at Schneider Electric in France, where I worked a lot on their internal IoT platform called EcoStruxure. So built a lot of things, saw a lot of problems in this space. Part of the challenges that I always saw in our team was the device side of things. It always taken a lot longer to develop, very difficult. Our cloud team got to move a lot faster, and the embedded team was always sort of the long pole in the schedule. And so that's something that we're pretty passionate about, and we're going to talk a little bit about how we help address that and make it easier for everyone.
Cool. And we literally launched the company. Been around for a little bit, but yeah October, November, but publicly, so, pretty much this week. But so you guys know the drill with embedded. I mean, a lot of this is when we're pitching to folks that don't know embedded, the challenges, and you guys have the skill sets. But there's a lot more people out there that don't know how to program embedded, don't know C. I know AI, I know I'm doing IoT, I'm programming in Rust or whatever, and of course there's a lot of stuff kind of converging even with the likes of Rust, in this space, but it's difficult, and the lock-in of silicon, and it's kind of the opposite of how we've been developing things in the cloud for some time, necessarily, but these devices, as we all know, they're getting more and more capable. We're starting to see more intelligence being put into them. Clearly, security challenges are on the rise. And then also, like, the people that know about, AI for vision, quality control in a factory are not the people that know necessarily how to program to an embedded device, or this person that knows about security or whatever. So bringing things together with different skill sets is difficult, especially, and in the embedded sense. And then, of course, just more and more in general, compute happening on these devices, and we're seeing SBOM. There's new regulations around memory safe code that are popping up, or at least guidance around memory safe code, and all of these factors are, we believe, are necessitating a modernizing how we approach embedded. And of course, we picked Zephyr for a reason, because it's a modern approach in general, but we're kind of building on top of it. So we joke at the company that the 90s called and want their tools back. We've seen a lot of change in the cloud over the years. Embedded, I mean, obviously there's been things that have happened in the embedded space, and Zephyr, again, is we think a really important step forward in a modern architecture, but embedded today, predominantly, it's kind of like, for embedded devices, it's kind of like server development was before VMware came along. And then, of course, you see Docker and Kubernetes and all that kind of stuff, functions as a service, and all of that evolution, as the cloud grew, now there's all this talk about edge computing and processing being more distributed because you can't send everything to a central data center. We're seeing a lot of these technologies now come back out into the field, but there's a practical limit to how far the cloud technologies can come as they are today. And clearly, WebAssembly has become very hot in the cloud native space, coming out of the browser. But we're seeing a bunch of activity in CNCF, and the Docker crew is talking about it, and a variety of things. But if you look at the continuum, this is a taxonomy from LF Edge. If you look at the edge as a continuum, well, first off, a lot of people say edge, and it's a misnomer. They're just confusing people. It's like, what's the edge? Well, what is it? people are like, what's the near edge and the far edge, which is funny because the telco would say near edge and far edge, but it's opposite of what you would think as a user, near edge, far edge, or thin edge, thick edge, and all this stuff. So the taxonomy that we did in LF Edge, this was like around 2020 timeframe, breaks it down into inherent technical trade-offs. And if you look at the continuum, the summary is I'm either in a distributed but still physical data center, regional data center, metro data center, on-prem data center. So I have a defined network perimeter. It's physically secure, and I can run Linux and Docker and Kubernetes and all that. Doesn't matter what the servers look like. It's just I have those tool sets. The next step down as you get into the smart device edge, as we defined it, was I'm out of a traditional data center, but I can still run Linux and Docker and Kubernetes and stuff. So I have to have a unique security model or zero trust security model. I have to assume I'm going to lose connection over times and stuff like that, and the like. So that's the next click down. And then the final click down is I'm out of the data center, I'm out in the wild, I'm basically embedded, and I cannot run Linux. I don't have the memory for it. So that's what we call the Linux barrier is it's generally, take like Docker with Linux, 512 megabytes of memory, maybe 256 is kind of like that lower limit on a single node. We're talking, of course, in this case, kilobytes of memory. So if you look at all the different technologies on here, like a Kubernetes, I was previously at Zedita. Zedita uses EVOS from LF Edge, so this Ocre will be a project right next to it. Even virtual machine projects like Zen and all that. All of these different tools are shifting left in the continuum, but there is that hard stop. They cannot go past the Linux barrier. What we're doing with Ocre is we're taking WebAssembly, which happens to be a really thin, lightweight, secure virtualization technology that of course started in the browser and then has been making its way into cloud tools. It actually provides those cloud-native benefits and extends past that barrier. So by combining Zephyr and WebAssembly, and we'll talk a lot more detail around the architecture, this project basically gives you the feel of developing for the cloud with OCI-like containers without having, but doing it on very, very constrained devices. So, so Ocre, it's not really an acronym, but it is Open Container Runtime for Embedded. It also happens to be it's a color, but then Stevens lives in France, and this is the French spelling of the color.
The acronym worked a little bit better. There's an H in the English spelling, so we couldn't figure out how to make H work.
So I'll have you get into more detail. I'll kind of give the high level. So this is a thin shim that sets up an environment to run containers in. An Ocre container, think of it as like Docker on a diet. So very lightweight containers that can be written in any programming language. You could take existing C code, lift it, and shift it up on top of the Zephyr runtime in a container, but then write new things in Rust or Go or whatever. 256K, of footprint. We'll talk more about performance as we go, but. So it really feels like cloud native, like your containers can sit in the same registries as a Docker container. It's really sort of approaching embedded from a cloud down mindset, and then you talk through all the the abstraction and whatnot. But so Ocre is that runtime. As we talk through it, we are donating this to LF Edge, so part of the Linux Foundation overall umbrella. Within the next couple months, and so we look forward to having folks be able to collaborate on it. The goal here is to make these containers kind of the equivalent of Docker for the embedded world. So with that, I'll hand it off to you to get into details.
So why containers? What's wrong with traditional embedded? And I think I'll start first and say, we don't think that this is appropriate for all traditional embedded. Things like your airbag and really safety critical systems, right? You're not going to want those containers. They're very different types of real-time systems. But there's a lot of embedded devices out there where this makes a lot of sense, right? And if you look at why would somebody use one of these devices, like I have here, which I know you can't see because of the way the podium is, but we'll show a photo in a few minutes. A lot of it has to do with cost. These things, are very cost effective. Moore's law has blessed them just as much as your PCs, right? So the power on these things is pretty impressive. But again, there's a number of these constraints that make it difficult. So on the right side, you have the traditional embedded. Generally, this is everything linked together, generally all done in a single build. Usually in a one image. Sometimes you might have a bootloader and a couple of loadable modules. I know we went to a talk earlier in this conference where we're doing some dynamic linking, which is pretty exciting technology. But in general, it's all linked together, right? So I need the source code. It needs to build with the same tool stack. I need to synchronize all that. Now, there's a couple core problems with that. First, all the IP, you have to have all the source code. So the IP is hard to keep separate, right? So if you're licensing code from a third party, you have to get that source license. In the open source world, that's not as big of a problem, but for some of the commercial stuff, for some of the other use cases, that does pose a problem. But also, because you have to bring everybody else's source code together, you need to make sure that you can compile it. And sometimes, somebody's using a slightly different version of the compiler toolchain than you are. And when you try to integrate those, you run into weird problems, different library versions, different toolset versions. And that just creates a lot of different friction. And again, you're also linking it into effectively a very, very large single image. So whenever there is even like a single line security fix, for example, you have to rebuild and relink everything, which means you have to retest everything. Right? So there's this big bang integration. You got to make that happen. And we can solve that with CI/CD, but you still have to test that, right? Provided you're being a responsible company doing the proper things to release software properly. And that's a huge amount of time. And then when you deliver that, you have to deliver that entire payload of bits to the device, which could cost money if you're on a metered connection, could be more risky because you're more time in the air. Some of these devices don't have enough space to store 2 copies of the firmware, so you're literally overwriting itself in there, so they can be really risky things. And what we've seen, I've seen in industry, I've seen it with customers we talk to, is people are very hesitant to update the devices because there's that inherent risk. And so it's sort of the opposite of what we want to have happen. We want to be really responsive to security. We went to a security talk today about what we're doing with Zephyr and being responsive and doing security reviews and stuff like that. Part of that is patching. But if it's risky to update those devices, people are really not going to go do that. So that's a huge problem with traditional embedded. That's sort of the negative part about that, but the other positive is if I can update the device, I can make it also much more software defined, right? The example everybody loves to use is Tesla. The features of the car evolve the longer you have it, which is not what you normally have with cars, right? So to be able to do this with these devices and have the devices improve over time, be more adaptive, and increase those features requires updates. And if updates are risky, people aren't going to do it, then you lose that business agility. So anyway, that's traditional embedded, and there's nothing wrong with that. There's just a couple of sort of realities that you have to deal with. If you look on the left, that's more like what you would see in a cloud-native application, right? You have an application broken into much smaller chunks, containerized, so these things are isolated. That allows you to put all those things into these neat little buckets that are much smaller, much easier to develop by a small team. And again, going back to that security, one-line security fix, there's a good chance it's probably only in one container, which means you only have to rebuild that one container, retest that one container. Obviously, you have to test it with everything else. But you have to do much less testing, and then you can update just that container. And if you look at how we do this in the cloud, we generally will do that live. We don't have to reboot the device, which is something you generally have to do with a firmware update. Also, if you're making these, if you're designing this to be much more modular, you can use the containers as a unit of modularity, which means you can then reuse those containers in different applications. So you can now actually do reuse because you're building these containers that have much more limited functionality. And again, you get a lot of those same benefits of I don't have to retest it, I don't have to do that. I can compose my application versus having to build everything and link everything from scratch. The other thing, though, is to enable that, you need a runtime, right? So if you look at what is done in OCI container, Docker container land, there's a bunch of supporting infrastructure around how that works. And when you start looking at things like Kubernetes, there's even other services there. So things like hardware abstraction, service location, container communications. Those are things that we provide in the Ocre runtime, and I'll talk about those on the next slide. So what does our architecture look like? As Jason said, we're based on Zephyr. We're technically RTOS agnostic, but we chose Zephyr for a lot of really good reasons. And we're really starting to take advantage of a lot of those. The biggest thing that we started looking at Zephyr for is the amount of board support that we had. It's very easy to get, I think we're up to like 575 boards. Then you have things like the device tree and device tree overlays, which makes it really easy to say, hey, I have a board like this, but my sensors are mapped this way, right? So we're taking advantage of that underneath, because that allows us to support a lot of this hardware. The other thing that Zephyr provides is a nice driver infrastructure, right? So you have a lot of I would say a lot of the same sort of concepts or abstractions that you have in a large operating system like Linux or Windows or Mac OS, but you have that in Zephyr, right? So there's good class drivers, for example, for various different devices. And now I can go and open that device, and how it's mapped to I2C or SPI or UART or whatever below can change, right? In fact, the part can change, right? So if I'm using an air quality sensor or a temperature sensor or a vibration sensor, how I use the sensor from the application perspective has this nice abstraction, and Zephyr gives us that. And then the actual underneath can be done with things like device tree support and the drivers behind that. On top of that, Jason mentioned WebAssembly. How many folks are familiar with WebAssembly? Cool. It's pretty confusing because it's probably not the best name for the technology. It's neither web nor assembly. It's kind of how I like to joke about it. It's basically a very lightweight virtual machine. It's the other thing I joke about is it's basically what Java promised 35 years ago, but actually delivered, right? So it's a lot of those promises. It actually runs on embedded devices nicely, right? But more importantly, it provides a true virtualization option here. And so we're using that as the core of our container runtime. So what runs in a container is WebAssembly code. Little star, we'll talk about that in a second. And that allows us to basically have code that can run across any architecture. So we can run on x86, because we can actually run on a simulator here with Zephyr. We can run on a board. I'll show this later. This is an ARM Cortex M4. We can run on ESP32, RISC-V, anything that's supported by that. There's a lot of wide support. And so that same container now can run across all of those, which is quite an interesting thing. So we have those two things. We have the base on the bottom, and then we have the container runtime. And that's good. That's like, now I can boot up on the device and I can run code. But that's not really a container runtime, right? That's just running stuff in a virtual machine. And so if you look at, again, how that journey of the cloud happened, it was when we started getting things like Docker and then some of the tools like Vagrant, and then suddenly things like Kubernetes that allowed us to manage this and orchestrate this and do it at scale. So that's what really Ocre is. It's taking those two technologies and building the rest of that out to create a real container solution. One of the developers on our team really challenged me early on, and we're like, is that really a container? And so we had to actually have a lot of internal debates about, like, what is a container? And what does it, like, what's enough of those properties in the embedded space to legitimately call it a container? And so I think, actually I'll jump to that, since I brought that up. We've actually done the comparison of that, because I was really challenged by one of the internal developers, and he was right. We really need to look at that. It's not just running code in some runtime. It actually needs to be something a little bit more than that. So in this chart, you'll see the two sides. I broke it down to sort of the normal things you'd see: compute, storage, networking, and security. So from the compute perspective, things run in a WebAssembly runtime. So that means it has to the build target is WASM or WebAssembly. Things are packaged as today they're packaged as a WASM module. That may change in the future as WASM and WASI kind of progress through the standards. But today we run a single module inside a single runtime instance. And then we schedule that behind the scenes with native threads. And we do have the ability now, but we will be extending that a little bit more to actually have multiple threads within the same container, right? Those will also be OS threads. If you look at what happens on the OCI container side, you have platform-specific code. It's compiled for a particular architecture. We have some fancy magic in OCI land for allowing to have multiple architecture containers, but that's really just a easy way to have multiple versions of the same container and reference it with the same label. And behind the scenes, it picks the right one of those. In our case, our code can run across all of those because WebAssembly provides that virtualization layer. And again, Jason was talking a lot about the Linux barrier. For containers to work and for compute to work, they're essentially processes, but they're walled off with things like namespaces and C groups and things of that nature. But they're run on that shared kernel. When you look at how their executables are packaged, it's basically a tar file system that gets expanded. Obviously, that's not going to work on an embedded device, which is why we're using the WASM modules. When you start looking at the other parts of the container, right? So that's the compute, that's the me running code and doing interesting stuff. But to support that code, you need things like storage, and you need networking, you need security. And what we did is we looked at what you can do with an OCI container and said, hey, that's interesting. It needs to be conceptually similar, but the implementation of that is probably not going to be, it probably can't be exactly the same. And so when you start looking at things like storage, well, on the OCI container spec side, you have things like this union file system, right? Where you expand all these tar files, and you have layers, and some of them are writable, some of them are not. And it's really complicated, and it takes up actually a lot of resources, and obviously that's not appropriate. However, the ability to have things like, I have an ML model that I need to load dynamically, and that needs to come down with my container, right? So I need to be able to reference that object, right? So we have the ability to have a very small simulated file system. So we're using a little FS for that kind of stuff. And also have things like blobs. So we can have binary objects in there. Those could be images, they could be ML models, they could be firmware images for downstream devices or other daughter chips and things of that nature, right? So we have the ability to reference those. Now, you're not going to get the full POSIX permissions and all that other stuff, because that's not appropriate in that space. On the networking side, again, the OCI containers, they're equally complicated, right? There's a whole virtual networking and network address translation and a lot of complexities. Actually, there's a lot of different options in there, and I still don't get my head around all of them. But massively flexible, but also lots of overhead, right? So even to just do NAT between like two containers on this kind of device is probably going to take up way too many resources. But the reason why those exist is for us to access outside network resources and to communicate between containers, right? And so those things we thought were the most important parts of that. So what we've built on our side is the ability to have marshaled sockets. So you can open up a socket with a standard socket call, make outbound connections, even open up server ports and listen. And then also we have a way to do inter-container messaging. So very simple, almost like MQTT, but it's all done through a messaging API. So that allows, and we'll actually show a demo in a little while about this, but that allows like one container to go pull data, pull something from a sensor, so go read a value, maybe do some hysteresis and debouncing and some data processing there, and then pass that off to another container that's going to do analytics, right? And so you can kind of build these pipelines of really useful things, just like you would do in the cloud with a microservice architecture. So again, that networking allows these containers to collaborate. And then from a security perspective, okay, on the OCI container spec side, you're looking at Linux, and there's a lot of things you can do. There's a lot of best practices. There's a lot of tools that are built on top of OCI and Docker and Kubernetes to do that. You have OS level protection in there as well. On the other side, in embedded, you generally don't have that, right? We're lucky to have, we have threads. We don't even have sort of process boundaries in a lot of cases. Some of these platforms have memory protection. Many don't. So when we started to look at that, like, well, what can we do? So the nice thing about having WebAssembly as a runtime is that gives us a nice security boundary, right? WebAssembly has this really good property of nothing can really escape outside of that container, right? So by default, if I just spin up a runtime for WebAssembly, I can do loops and math and comparisons, but I can't access the file system. I can't access the network. I can't do this. And this is true in the browser. This is true on our embedded platform as well. The way you make that useful is you inject interfaces into it. You inject these APIs that are then available in there for that container to call, all right? So for example, we can inject an API to open up a socket, right? But that call is marshaled by our runtime. So what that allows us to do is it allows us to have security controls over that, right? And so we can actually, in our container manifest, say, hey, the code in this container can access the file system, can access the network, right? But if it tries to go do something else, we'll block that call, right? So if it opens up a socket, yes, you have the permission, you allow that to happen. And so when you look at things from a security perspective, it makes it easier to build defense in depth, for example, design that into your product, right? Because you now can say, hey, this thing can access the network, this can't. This can access storage, but these can't. The other thing that we can do is, just like in big OCI containers, we can do image validation. So I pushed code down. I know, Cedric, in your presentation, there was a question about, like, hey, if I can dynamically put code on this device, I can dynamically put bad code on this device. And how do I ensure that that happens? And so if you look at how that's done in the Docker world, they use digital signatures and certificates and cryptography to say, hey, you can only run code that's signed by this particular certificate. And we can do something similar here as well. Let me go into performance, and then I'll probably jump into demo because I think it's interesting.
Yeah, we got 15.
15? Perfect. So I go through this presentation, a lot of folks are like, that's great, but you're running a virtual machine on an embedded device. The performance must be terrible. The truth is, it's actually not that terrible, right? For normal interpreted WebAssembly code, we're about 5-10 times slower, right? Which sounds horrible, but that's for really CPU-bound code. If you're writing an application that's reading from a sensor, doing some simple analytics, maybe doing some data conversion and sending a stream of data up, which is kind of common in, say, a condition monitoring industrial application, the performance delta between those two is going to be very, very minimal. Now, that said, we weren't really happy with that level of performance degradation. For a lot of applications, especially when you're talking about AI and ML, that even a 5x hit, it's untenable, right? It's not gonna be something that will meet the performance requirements, right? Or somebody will have to buy a much more expensive board that has a lot more CPU power, and now you're in that class of closer and closer to Linux-capable devices. So what we've done on our side, and this is part of the Atym commercial product, is we have the ability to do ahead-of-time compilation. Because we know the CPU architecture that we're deploying to, we can actually take the WebAssembly and do ahead-of-time compilation. And that gets us to darn near close to native performance, because it literally is native code. So slight overhead on that, but for hard CPU-bound applications, it's like a 20% slowdown, right? So we think that that's really, really good on the performance side of things. We also have the ability to run absolutely native code. And so for things that really need to be accelerated, things like neural networks and some of the AI stuff, there is standards within the WebAssembly world. Example of that is called WASI-NN. Dan from Sony Midicora talked about that. That allows you to have an API and then have all completely native optimized accelerated code underneath. So we do have that as well, if for those applications that truly need that last little bit of performance out of there. The other question people have is like, that's great, but these containers must be big. They must be, they must have some other overhead. They're actually incredibly small. So I'll show you a couple of different applications today, but our smallest individual app is about 300 bytes. Not kilobytes, actual like 300 bytes. And I was actually doing this demo before, and I was like, why is this 1,000 bytes? It turns out that I was printing a very large string. And so the 1,000 bytes was actually the data in there, right? So the overhead of this is pretty low. And the reason for that is a lot of the common code that you would normally call, like libc and all those other functions, are in the runtime. They're part of Zephyr, right? So we don't have to link to those, right? So we just have effectively the code that somebody's writing in there. A few tricks we have to play with the compiler to sort of say, hey, don't link in libc, don't do this, and do some optimizations. But we literally can get this down to about 300 bytes. And I've done this in both C, and I've done this in Golang as well. Not done this in Rust yet, because I'm still learning to understand Rust. So let's see, anything I missed on that? And I mentioned before, we can run this on pretty much any processing architecture. ARM, we can run on something as small as a Cortex M3. We run really well on M4 and M7. We can run on Tensilica, so the ESP32 platform, which is an amazing platform for the cost. We can run on x86, so you can actually run our runtime on a PC, so you can actually do development on the PC without the hardware and have all that simulated, do some debugging and whatnot. And we can also run on RISC-V.
And actually, one of the questions we get often is when does the relevance stop as you look at the continuum from, we're making it possible to run containers on lightweight devices. When does it stop? But we're not trying to be Docker or Kubernetes or whatnot with this project, but if you bleed up a little bit, well, I just gave you 256, 512 megabytes of memory to do something else with, where that costs you money on your BOM or whatnot. So we do believe there's going to be some bleed, but it is optimized for this class of device. Yeah,
there's like the Raspberry Pis of the world, which are quite literally faster than like mainframes when I studied in university, right? They're pretty like little mini supercomputers, right? Compared to these devices. But there's a set of application level chips out there, that are Linux capable, that have some of those resources, but as you say, just don't, they kind of fall in that space where that's just not enough to do the kind of things you want to do on that. And so our stack is being as small as it is, gives you a lot more headroom there. And I think that's pretty, it's going to be a really interesting space for some of those applications. And yeah, I talked through this before. I don't think I need to go through this. This is mostly about WebAssembly. The one thing I'll say today is there's a lot of work going on in well, it's a little bit confusing. There's WebAssembly, which is the runtime in general. That's the language, the virtualization. That originally started in the browser, and that still has a lot, that's where a lot of that comes from. There's a subgroup called the WebAssembly System Interface, or WASI for short, and that's where a lot of the work outside of the browser is happening, right? So you hear the likes of Cosmonic and Fermyon, and I can't remember all the names, but there's a lot of them out there that are building things that run on server class hardware, but are running that runtime, that WASM runtime outside of the browser. It's sort of the distinction between, say, JavaScript and Node.js, right? In that WebAssembly group, it's very, very active. There's a lot of work to go on about, like, what is the platform? What should the platform that is WebAssembly outside the browser, what should that look like, right? What calls should be available? How do we structure that? And so we're part of that community. We're working really closely with that. In fact, we're working on an embedded special interest group within that to define how does this platform look like? What does that platform look like? And so some really interesting things going on there. It's an active space, so if you want to get involved, we'd love to have participation there. Okay, with that said, I'm going to jump to the demo. And unfortunately, you really can't see. So that is over here. It's at an angle, and it's a little bit difficult to see. But I'm going to run through a couple of different demos here, showing you some of the capabilities, the typical Hello World app, but then I'll show you something more interesting. The setup we have here, the green board is a Nordic Semiconductor NRF 5340. So it's a Cortex M4. I think this one has 384K of memory and about 2 mega flash, something like that. The board you see on the bottom, this one here with the red LED, that's actually the modem. This board for this particular dev kit doesn't have Wi-Fi, so that's the Wi-Fi chip. And then the purple board next to it is a proximity sensor. So let's go and, oops, I'll give you the summary. Let's go show you a demo. Okay. And that is readable. Excellent. All right. So this is our platform booting. So obviously you see the Zephyr OS. You see that the Ocre project started. And again, I mentioned before, we know what the target is. So that allows us to do optimizations. And in our commercial product at Atym, we understand that, and we can optimize things in the cloud because we know that target. And then you see the runtime started. So right now, this device has no application assigned to it. And if the network gods are kind to me today, we can go deploy something. One of the things that we tried to do is, again, we're trying to do containers on microcontrollers. And people already understand, they already have a mental model of what containers are. So we want this to be as similar as possible. Obviously, the implementation details aren't the same, but we want commands to be very similar. So here we're using our Atym tooling. So I'm just going to say Atym run, just like you would do Docker run. And then I have a container called Hello World on latest. And the only thing different, and so normally this is what you would do with a Docker container. But in this case, I have to actually tell it what device to do. And this one's surprisingly called device 2. Right? So that's going to go out there. What you'll see is periodically the management agent on our platform, again, if the networking is working, will pick up the fact that there has been an update and automatically download it. I am cheating, just to be careful. I've pre-downloaded the apps for this demo just because I didn't know if I'd have good connectivity. So it's actually getting this from the cloud, but the images are not downloading live. We can do that later if you want. So as you can see, this is just the Hello World app that we have, right? So you'll see that it found that there's something to download, and then our entry point for our containers is this method that you have to expose called oninit. We can look at some of that code later. And so this is just doing a bunch of printfs. Again, nothing all that exciting. But one of the interesting things is, as Jason said, one of the cool things in the cloud is to have, with containers and cloud native, is to be able to use the right tools for the right job, right? If I'm writing network services, maybe I want to do that in Go. If I want to do AI and machine learning, I'm probably going to do Python and some other, PyTorch and things of that nature. So let's do something interesting, right? Let's run this Hello World app, but let's do it in Go. And so this is similar to the other one. Sorry, I should give it a little bit more fanfare, but Hello Embedded Source Summit, right, written in Go. And so this is exactly the same kind of printf, but actually done in Go. And we're using standard Go toolkits here, so there's no weird stack. That's another advantage of us using WebAssembly. We don't have to build the tool chains. We don't have to build a compiler stack. We do have to sort of tune it a little bit in towards like what our compiler flags are. Like, so for example, to get this down to be as small as it is, we're using TinyGo instead of Go. And we're also disabling the garbage collector, because in this case, we actually don't need the garbage collector. So like, that allows us to get that down. But that's the standard TinyGo compiler. You can go get that from the TinyGo folks. And you can do the same thing with Rust. Rust supports this out of the box, so you don't need to do any of this. Not the most interesting app, so let's do something a little bit more fun. So here, I'm going to run this thing called the proximity demo. And I got to tell it to run on my device. What this one does is it reads from the sensor periodically, and then it prints out both the distance that the distance sensor is indicating, and then some little bars so you can kind of see that. Okay, and so it's not done anything. So as I get closer to this sensor, you'll see it suddenly, right? And so this is really interesting because I'm doing all this code from within the container, and it's calling out through our runtime to a Marshall call and then going down into the driver stack of Zephyr, right? So that's not just hello world in a container and I'm running that, and it's not talking to anything in real hardware, right? So I can do that. Okay, so that's that. All of these have been single container demos. So I'm running a container, and then I'm replacing that container. You might have noticed that I didn't actually have to reboot. I can do this live, which is kind of interesting. In the real world, you may not want to do that, right? There may be some synchronization you might need. You may need to want to start the container up in a particular fashion. So you may not choose to do that, but you actually have the ability to go do that, right? And I'll show you something interesting in a second. Actually, sorry, I have a script for this. Okay, so here I'm going to deploy a multi-container app. This will take a couple of seconds to run. So what we're doing here is we have 3 containers. So we have one container that's reading from the sensor, called the sensor service. We have an analytics service, which is doing a very simple analytics, it's doing thresholding. And then we have an alerting service, which is doing that, and so which is responding to those analytics. And so in each of those cases, we actually are sending messages between them. So the sensor service is reading from the sensor, getting a valid reading, passing that reading over basically a queue to the analytics service, which is then doing its thing, and then only then is it sending alerts to the alert service. In this case, the alert service is just printing that to the screen so we can actually see what it's doing. But in the real world, you might, this is a proximity thing, so it might be if I get too close, it might shut the machine down, right? If you've seen big, large machinery, a lot of times there's sensors with proximity sensors where if you stick your hand in the machine, it could get cut off, and so the machine will automatically stop, so it'll detect that. So that's the kind of thing you could do with this. In this case, I'm just printing something out. So the demo gods are coming to me. You can see, right? It's telling me I'm too close. But the really interesting thing is there's actually a bug here, which I didn't do on purpose, but then when I discovered I had a bug, I thought it would be a better part of the demo. So the way this is supposed to work is it's supposed to say warning when I get near it. And come on. All right. But it's actually saying critical. And then if I get really close, it's supposed to say critical. Right? So I have the logic backwards. Well, that's dumb. So let's go fix that. So in this case, I'm just going to update that code, right? So the other 2 containers are the same. I just fixed my bug in my container, in my middle container, and now the app is restarted. Now it should say warning, and then critical. Right? So it's like super sensitive to. I probably should have picked one that had a bigger throw on it, but all right. So anyway, that's multiple containers, talking to real sensors, and doing some actual work on that. I think that's it. Actually, there's one other one, since I have probably another 2 minutes. Actually, yeah, let me do this one. Run. Okay, so this one I'll actually have to download, because I didn't pre-download this, since I actually got the network working. So you'll see in a second, it'll detect that there's an update. I think it's like every 10 or 15 seconds it'll check in. Okay, so it's starting to download that, right? So it is now in the background updating this, but at the same time, this application is continuing to run, right? And you'll see that it just exited, and so now this new app is going to take over, and it just blinks the LED, right? Every 5 seconds or so, right? So you can see we can actually do that live, and we can change that dynamically. You can unload and reload. So anyway, that's that. Let's go back to the present. Oops, hold on. I gotta go back to our presentation. Yeah, I gotta find this button. I knew I'd do that. Sorry. I don't know why I had to do that, didn't I? Come on. All right, I can't see that screen. Sorry. Yeah, no, I got it. No, actually, no, you went to, yeah, right there. Perfect. Sorry, I can't, I have a different screen. So anyway, Ocre is our container runtime. It's tiny. It's designed for this class of devices, right? We're talking, as Jason said, something that's 1,000 to 2,000 times smaller than, yeah, you're. Oh, hold on. I don't know why it's not doing the. Hello? Is it not? Is it not over there? Oh, I know what happened. Yeah, there we go. There we go. You know, I should have used yeah, I should have used Linux, not Windows, at an open source conference. All right, so anyway, in summary, yeah, so Ocre is tiny. It's designed to run in these devices. So we're talking 1,000 or 2,000 times slower than what you would, sorry, smaller than what you would need for Linux and Docker. We're using a lot of open source technology as our core underneath, and then we're building that framework that allows us to have a true container and satisfy the challenge for my developer. We're going to be dropping code somewhere in the June timeframe, maybe sooner. And then obviously stay tuned for more details. But you know, we're looking for people to get involved in the project. We're looking for people to contribute. We're looking for people to use this and provide feedback and all that. For the moment, you can send us an email at info@atym, atym.io. We'll add you to the mailing list, and then we're in the process of getting the project website up, the wiki, and then obviously the code drop. And so once that's done, we'll add you to our mailing list, and we'll go from there.
Yeah, even before the June timeframe, we'll have the structure set up within Linux Foundation and whatnot. So that's for like right now if you're interested in learning more. But we'll get the structure set up, and then the code will be in there shortly thereafter. And we're working on tying this to the special interest group and the WASI community. Of course, we want to collaborate closely with Zephyr, but this is really about kind of taking a new approach and opening up embedded, we think, to a lot of new developers that don't have the skills that a lot of you guys have. So do new things on these types of devices.
Perfect. And then, oops.
Cool. I don't know if we have, I think we're over. Do we have time for questions?
1 minute.
1 minute.
Do you have any questions? And then we can always go outside. So, I think it's on. Just.
Yeah, thank you. This looks wonderful. What's the memory management model for this? Like, how do you constrain the memory that these applications will be using?
So there's the answer that is today, and then the answer that we're going to be marching towards. Today, there's a fixed amount of memory that's allocated per WebAssembly instance. when we create a container, we create a WebAssembly instance. So when we're running 3 containers, we actually have 3 different instances of that. Each has its own address space. Today that's fixed. It's actually a compile time thing that we can put in there. So we can sort of tune it a little bit. Where we want to go in the future is in our container manifest, we want to have the ability to say, I need about this much memory, right? And then we can dynamically do that. The runtime we are using, the WebAssembly micro runtime, does support some of that. It just doesn't do it quite as dynamically as we need to yet, at least in our runtime. So we're going to make that so that it can be tunable. Part of the other thing we want to do as well is provide some analysis tools to kind of give you some guidance as to what should it be. And fortunately, there's a lot of work going on in the WASI groups around how much memory do we have to allocate, right? So the folks that are doing this on the server want to pack a lot of that into a small container. So they have exactly the same problem, but it's a different order of magnitude, but they're trying to do that as well. So we'll be able to take advantage of that tooling. So,
cool. Thank you very much.
Any other questions?
Did you have a? Oh, go ahead. No, go ahead. I was just curious if the interface from your host telling a container to run is the only interface, or if there's an interface from the other side. If suppose I wanted to have my application launch containers and approach it from within the Zephyr side of things.
That is exactly why we want to have a community open source project for those kind of things. So actually, it's not difficult for us to expose that. We probably want to put some security around that so they could be a really good vector for attack. But in principle, calling an API that allows you to run another container is something that's pretty straightforward and easy for us to do. And we would just have to create an API for that, and then obviously the implementation behind that. One thing I didn't talk about, though, is actually with the sensor service, the container's not running most of the time. It's not just sitting there running in a loop. I have an interrupt and a callback. So I can say, hey, because we have a nice sensor API in Zephyr, I can say, hey, when that signals, call this API. And so our sensor API actually calls a different method that's been registered into the container, right? So we have that both calling kind of conventions where it can go call and do something, or we can call into the container. So cool. I think we got 30. Yeah. No, all right. Yeah. I'll start packing up.
So I might have missed the beginning, but how do you actually deal with like accessing a register, or let's say you need to access some custom I/O? How do you actually do that? Do you have to have a helper on the Zephyr side?
Yeah, so we have some marshalling code on our side that interfaces with the driver stack, and so we have to build and wire in all the sensors that we support. So we'd have to explicitly build support for that. We will have the ability to do custom for a customer or somebody using the project to actually build their own and then link that in themselves, right?
So will there be some kind of standard if you want to run that on 3 different platforms that you can have the same marshalling stack on all those platforms? Or I mean, at least at the top,
Zephyr solves a bunch of that for us because we can take advantage of the driver stack there, and then our marshalling code is largely the same. You'd have to write new marshalling code if you have a different type of device, right? So, but we have support for things like GPIOs, I2C, SPI. So we're going to build a lot of those, and then obviously there's no end to the number of peripherals that somebody can dream up. Sure. So some of those we'll have to we'll build it as part of the project, or somebody will have to build their own custom ones. So.
Okay, thanks.
You're welcome. Thank you. All right, appreciate it. Thank you. And then we're around, please contact, or we can chat in the hall.